Hello, welcome to Econometrics Melody. In this video, we'll discuss about the gamma distribution. Before that, let us see some of the useful functions. They are useful either to calculate the PDF or the CDF of the gamma distribution. Exponential and logarithm, they are inverse to each other. That is why we are going to get the value of factorial 5 in the first case and the value of gamma in the second case. And we want to show that gamma n is equals to n minus 1 factorial. Therefore, the value of gamma 6 is equals to 5 factorial. And the value of gamma 9 is equals to 8 factorial. They are the same value, and the value of gamma 12 is equals to 11 factorial. We don't get the result. We cannot calculate the factorial of any decimal numbers. Here the value of factorial 3.5, we didn't get any value, but we can always calculate the gamma of any decimal value. So gamma 4.5 is equals to 11.631728. Now let us see some of the useful formulae of the gamma distribution, and we will explain it as well as we'll find the PDF and CDF of the gamma distribution. We'll calculate both of them. First of all, we are going to talk about the A. A is our shape parameter, B is our scale parameter, and G is our location parameter. The location parameter, generally it comes in the deviation form in the formula, and the scale parameter, it comes in division form, while as the shape parameter, it comes in the index form. Now let us say its mean. The mean or the mu of gamma distribution is A into B, the product of the shape parameter and the scale parameter. Variance is equals to A into B square, and its PDF is equals to x to the power A minus 1 e to the power minus x divided by B, and whole divided by B to the power A and gamma A. We calculate the CDF of gamma distribution by this lower incomplete gamma function for the parameter A and x divided by B whole divided by gamma A. And gamma function, we can calculate the gamma function in its integral form by integrating 0 to infinity for this variable z, t to the power z minus 1 and e to the power minus t, integrating it with respect to t, change of t. Gamma z can be written as z minus 1 factorial, which we have seen in our earlier example. Gamma z can also be written as z minus 1 into, again, gamma function of z minus 1. Gamma function is complete when we integrate from 0 to infinity. Here 0 is our lower value and infinity is our upper value. So for any value x, if we integrate from x to the upper bound, let us call it infinity, so upper bound, this will be termed is upper incomplete gamma function. And if we integrate from the lower bound to certain point x, then it is called is lower incomplete gamma function. And lower incomplete gamma function is useful to calculate the CDF of the gamma distribution, which we will integrate. We'll find the value of the integration to calculate the CDF of gamma distribution by the help of example as well. And now let us move to the next section and calculate the CDF of the gamma distribution. We'll calculate the CDF of the gamma distribution by taking help of quadrature class in Mata, and we will show it, and we'll calculate the CDF for these three examples. And the quadrature class is supported from Stata 16 onwards, I guess. So I'm using Stata, the version Stata 17. So first of all, we are going to calculate the CDF of gamma distribution when the shape parameter A is 5 and for the value of x to be 6. We will discuss the quadrature class in detail in our another videos. Now we are here, we need to set up certain function x to the power a minus 1 into e to the power minus x, and we integrate it from 0 to certain value of x. Here it is 6, that is why it is called as lower incomplete gamma function. First of all, let us run it, and what value do we get? 17.1586644. So this is the lower incomplete gamma function divided by gamma 5. Gamma 5 here means gamma A. So this is the generic formula to calculate the CDF of gamma function. And another gamma P, it is the Stata function to calculate the CDF of gamma function. So for the value of x less than or equal to 6, the probability is 71.49%. Now let us see another example. This time we are going to take the value of A, shape parameter, to be 1 and the value of x to be 0.7. Again, we have this function x to the power, here we have a, the shape parameter a minus 1 and e to the power minus x. This is our function, and we are going to integrate it from the lower limit 0 to certain value of x 0.7. That is why we called it as the lower incomplete gamma function. Let us see what does it yield. 50%, 50.34. The CDF of gamma distribution is lower incomplete gamma function divided by gamma, and this is the value of a gamma a. So let us see, both of them should yield the same result, and it is again 50.34%. Now let us see another example where we have the shape parameter a to be 12 and the value of x is 10, and we have placed in our function the value of a to be 12, and the integration, we integrate it from 0 to the value of x is 10, and let us run it. What does the integral value do we get? So it is this big value, and this is the lower incomplete gamma function for the given parameters, and we divide it by the value of gamma 12 is our a, gamma a, or the same parameter, and let us run both of them. We should get the same result, 40.32%. So we have already seen it. Now let us see these examples once again and see its graphical representation as well. So the probability of getting 6 or less than 6 is 71.49%. 6 or less than 6, it is 71.49%, somewhere over here. And let us see another example. We have already calculated it, and it is 50.34% for 0.7. 0.7, it is somewhere over here, 50.03%. Similarly, for the value of x is less than 10 for the given parameter, say parameter a to be 12, what is the probability? We calculated it to be 30%, I guess, and for x less than 10 it was somewhere 30%, somewhere over here. Now let us calculate the PDF of the gamma distribution, and let us see it by the help of both examples. Gamma, then it is the Stata function to calculate the probability of exactly x to be certain value. Here it is 6 for the given parameter. This is our shape parameter, scale parameter, and the location parameter, and this is our generic formula. Here it is x to the power a minus 1 into e to the power minus x divided by b, and here it is b to the power a and then gamma a. Let us see, both of them should yield the same result. Both of them should yield the same result, and it is 13%. The probability of x to be exactly 6, it is 13%, and let us see it by the help of the PDF graph as well. X to be 6, it is 13%. For the value of x to be 6, it is 13%, somewhere over here, 13%. So here 3 different distributions are depicted in a single graph. At the backdrop, we have a normal distribution with these parameters, and the graph with this red line, it is our gamma distribution with the given parameters, and with this dotted line, it is our chi-square distribution. Now let us see another example where our shape parameter is 7 and the scale parameter is 2 and location parameter is 0, and for the value of x to be 12. So what is the probability of getting 12, exactly 12? And by both of the formula we should get the same value. It is 8%, and let us see it by the help of the graph. For 12, x to be 12, it is 8%, and we have 12, it is somewhere over here, 8%. So at the backdrop, we have a normal distribution with the mean and variance equal to the mean and variance of this gamma distribution. And if we look at it, the gamma distribution and the chi-square, they both have merged or coincided. So the gamma distribution, it produces the chi-square distribution when the scale parameter b is exactly equals to 2 and the location parameter is generally 0, and the degrees of freedom of the chi-square distribution is twice the shape parameter. Now let us repeat the same process, but this time our shape parameter is 6 and our scale parameter is 2.1, location parameter 0. What is the probability of x is 10, and let us see, both of them should yield the same result. It is again 8.3%, and let us see it by the help of the graph as well. So over here x is 10, I guess, and this it is 8%. The red line, it represents our gamma distribution. This dotted line, it represents our chi-square distribution and the normal distribution at the backdrop. Now let us see some of the simulations, and in the first case we are going to change the shape parameter a from 1 to 12, and our scale parameter is 1 and our location parameter is 10. And let us see what kind of graph do we get. So the shape parameter, it increases from 1 to 12. If the shape parameter increases from 1 to 12, we see that it has a tendency of converging with the normal distribution. This is what we want to show. And let us see another simulation. This time we are going to increase the shape parameter from 20 to 60 at the rate of 3. The change rate is 3, and for the scale parameter to be 30. If we look at the nature of the graph, there is some tendency. If the shape parameter it increases significantly, then there is a tendency of it converging to the normal distribution. Now let us see another example where we will increase the value of b, that is our scale parameter, and as the value of b reaches 2, that will converge with the chi-square distribution. The gamma distribution will converge with the chi-square distribution. Here at the backdrop with this faint brown color, we have a chi-square distribution, and when the b reaches 2, it will converge with the chi-square distribution. So here is the scale parameter, is the scale parameter is 2, so it has converged with the chi-square distribution for its degrees of freedom twice the shape parameter. Now let us repeat the same process, but this time we are going to take the shape parameter as 12, and let us see how the gamma distribution will convert to the normal distribution when the scale parameter reaches 2. It is 0.75, and at the backdrop we have this faint call, and at the backdrop we have the chi-square distribution. So with the faint brown color, we have a chi-square distribution with the degrees of freedom 24, and therefore the gamma distribution with half the degrees of freedom of the chi-square is its shape parameter a to be 12, and when b reached 2, so the gamma distribution it converges to the chi-square distribution. Actually, chi-square distribution is some condition of the gamma distribution. Let us reinforce this concept, but this time we are going to keep the shape parameter to be 90, so we should get the chi-square distribution 180 with the degrees of freedom 180, and they will converge. So we have a chi-square distribution with 180 degrees of freedom, and we see the gamma distribution a is equals to 90 and b is equals to 2. This yields the chi-square distribution with the degrees of freedom 180. And if we see the nature of the graph, is the shape parameter it is increasing, we see that the distribution as a whole converges to the bell-shaped curve. Now let us talk about the hypothesis testing, one-tailed test, and we have written a program called gamma area. So at the backdrop we have a normal distribution with the mean and variance equal to this gamma distribution, and x is equals to 1, it is our null hypothesis, and we want to test a one-tailed test whether x is less than 1 or whether x is greater than 1 depending on our question. Now let us see, the left side it covers 8% and the right side it covers 92%. So in either of the cases we fail to reject the null because the p-value in both of the cases is greater than our alpha value of 5%. That is why we fail to reject the null, and we conclude that the value of x is in fact 1. Now if a certain process follows a gamma distribution with the shape parameter is 6 and the scale parameter is 1 and location parameter is 0, and we want to test the hypothesis with the value whether the value of x is 5. Our null hypothesis x is equals to 5, and we have two alternative hypotheses, whether x is less than 5 or x is greater than 5, and if we look at their p-value, they are again greater than our alpha value of 5%, both of them. So in either of the cases we fail to reject the null, and we conclude that the value of x is equals to 5. Now let us see another example, and where a process following a gamma distribution has a shape parameter to be 2 and its scale parameter is 1 and location parameter 0, and we want to test whether the value of x is 6. It is our hypothesis, null hypothesis, x is equals to 6, and alternative hypothesis x is less than 6 and or x is greater than 6. Depending on the situation or according to our question, we will test only one alternative hypothesis. For x is less than 6, it covers 98%, so in this case we fail to reject the null. And for our right-tailed test, the p-value is actually 2%, which is quite less than our alpha value of 5%. That is why we reject the null. And for the right-tailed test, we conclude that the value of x is in fact greater than 6. Now let us see another example, and we want For the shape parameter age 1 and scale parameter also 1, location parameter 0, and if it's a gamma distribution and we have to test the null hypothesis whether x is equals to 3.5. X is equals to 3.5, we have two alternative hypotheses, either x is less than 3.5 or x is greater than 3.5. Let us say for our left tail test, the p-value is 96%, which is greater than our 5% alpha value. That is why we fail to reject the null in this case, and we conclude the value of x is 3.5. But for another alternative hypothesis, if x is greater than 3.5, our p-value is 3, which is less than our alpha value of 5. And if we have taken our alpha value as 5, then we reject the null in this case, and we conclude the value of x is actually greater than 3.5. But if we take our alpha value as 1%, then our p-value is quite greater than our alpha value. Then in that case, we would fail to reject our null and conclude that the value of x is 3.5. Now let us see some of the uses of the gamma distribution, and I've collected it from different sources. The first one is the property. In fact, the gamma distribution is a flexible distribution that can take on a variety of shapes depending on the values of its parameter. And gamma distribution can be used to model both symmetric and skewed distribution, and can be used to model both light tail and heavy tail distribution. Some of the examples of gamma distributions applied in different fields like actuarial science, to model the distribution of claim sizes in insurance, in astronomy to model the distribution of luminosities of galaxies, and in economics to model the distribution of income, in medical research to model the distributions of disease progression or treatment response, in ecology to model the distribution of a population size, and it has a wide range of uses in various fields. So this is it for this tutorial. Thank you very much for your time. Thank you very much, Econometrics Melody.